Let's look at kurtosis. Let's start with the equation here. So we have alpha sub 4, because this is the fourth statistical moment. And we're going to take each observation, subtract from them their own mean. And since this is our fourth statistical moment, we're going to raise that to the fourth power, sum that up, and divide it by n times the standard deviation to the fourth power. And to recenter everything back on 0, we're going to subtract 3. Okay? So let's look at a normal distribution, or a nice smooth bell-shaped curve distribution, and see what this does. All right, we have our mean, which sits here in the middle, and I'm going to mark off our 3 standard deviations in either direction here. But this is the mean. Oh, sorry. This is the mean, right? That is this center line right here. And the more deviations we get from that, so let's say that this is less than 1 standard deviation. So we're talking about this area right here. All right, and let's say that we have a standard deviation of half. We have an observation that sits right here, -5. When we raise that to the fourth power, that half, when we square it, it becomes a quarter. When we cube it, it becomes an eighth. And when we raise it to the fourth, it becomes a 16th. So any value that is within 1 standard deviation of the mean, by the time we cube it, by the time we raise it to the fourth exponent, gets so close to 0 that we're essentially ignoring anything in this area. Anything that happens within 1 standard deviation of our mean, we are essentially ignoring, okay? Anything in the tails then gets exaggerated, right? Well, anything that was at 1 doesn't change at all, right? Because 1 to the fourth is 1, so that doesn't change at all. But anything that happens in our tails gets exaggerated, right? If you were positive 2, and once you raise that to the 4, it becomes 2, 4, 8, 16. Right now it's a very large value. So we are exaggerating the tails and ignoring what's happening in the middle. And because we're cubing it, we're losing our signs. So we're not comparing negative tails to positive tails. We're just summing up how big are the tails. So kurtosis really is a measure of how big are the tails. How big are the tails? A value near 0 means that we have a nice smooth. So if we have a kurtosis of 0, then we have a nice normal distribution like the one that we're looking at right here. Okay, let's make a little bit more room in here. Erase all my artwork. Okay. If we have tails that we have very large tails, so that if we have a distribution that looks like this, okay, we would call this a leptokurtic distribution. And that means that we have, it's becoming increasingly positive, a large positive kurtosis. The word lepto means slender, and so it's the idea that we have now this slender distribution happening here in the middle, right? But remember, we're not actually measuring the peakedness. We're not actually measuring the peak, we're measuring how big these tails are. And when our tails are really big, when we have large tails on both sides, then we have a leptokurtic distribution, meaning a slender distribution. We could also have the opposite, where we have sorry, that's very ugly. Where we have a distribution that goes more like this. And we would call that a platykurtic distribution. And that would mean that we have an alpha sub 4, or a kurtosis that is negative. Okay, and all that means is that we don't have big tails. All of the weight is incorporated here in the middle, which we're ignoring, remember? So we do not have big tails. That means platykurtic. The word platy means flat, like plateau or the tail of a duck-billed platypus, right? It means flat. So if we have a negative value, that means that we have a flat distribution. If we have a positive value, that means we have kind of a peaked, slender distribution. And if we have a value near zero, then we would call this a mesocurtic distribution. That's what happens when we have near zero. And meso just comes from the word middle or moderate. So that's just our normal standard bell curve. Okay, so kurtosis is really a measure of how much is happening in the tails relative to what's happening in the middle. All right, let's calculate kurtosis. I'm going to go up here to miscellaneous and change working directory. That's where you find it on a Mac. On a Windows, it's under File and Change Working Directory. I'm going to go to the folder in which I have saved 3 variables that display varying levels of kurtosis. Okay, so I will open those up. Now that I've set that working directory to the right place, I'm going to open this up. I will call this the data. And I will open it using the read.csv command, and the data is called kurtosis.csv. So let's make sure that opened. Yeah, that is opened correctly. I sent that over by highlighting the line, and on a Mac holding down Command and hitting Return. On a Windows machine you would hold down Control and hit R. Okay. So let's take a look at what we have here. Dim the data. That'll give us an example. It'll show us what the dimensions of the data are, and we can look at the names of the variables using the names command. So we have 250 observations and 3 variables, and our 3 variables are platy for platykurtic, meso for mesocurtic, and lepto for leptocurtic. So this is our flat distribution, this is a moderate distribution, and this is a slender distribution. So the easiest way to calculate kurtosis, and we'll do this for each of those 3 variables, is that inside the E1071 package, there is a variable or a function called kurtosis. And so I will highlight these 2, this to open up the package, and the bottom one there to apply the function to the meso variable. And when we zoom in here, we can see that our mesocurtic data set has kurtosis very near 0, which means it's a very normal middle ground distribution. If I want to calculate kurtosis for the 3 variables at the same time, I could use the lapply function. And the lapply function just applies to all the variables in this data set this function. So it will calculate the kurtosis for the 3 variables. I'll send that over, and we can take a look at what we've got. So our platykurtic has a significant but not dramatic levels of kurtosis at -0.9, almost -1. Our mesocurtic is near 0, which is what we expect for kind of moderate levels of kurtosis, and our leptocurtic distribution is 1.5, so quite a bit stronger and more peaked. If we look at the, we can plot these. If we, let's see, let's plot the density of the data lepto. Okay, so you can see that we have tails here on both sides, and we have kind of a nice slender, well, nice maybe is subjective, but we have a slender distribution indicating that we have a leptocurtic distribution there. If we look at our mesocurtic distribution, this is our nice normal bell-shaped curve. And if we looked at our platykurtic distribution, you can see that it's flat, right? All of our material is here in the middle, and we don't have very much going on in the tails. Okay, so this is the easiest way. The kurtosis function inside the E1071 package is the easiest way to calculate kurtosis.